now we do Fibonacci. We got 0 as our starting number in this description. F0, so meaning the first iteration of the sequence, right? It starts at 0, okay? So we go here, F0 is equal to 0. And then we got F1 is equal to 1. So all we know to start with is that F0 equals 0 and F1 equals 1. But the next numbers of the sequence are what it starts to get important. After 1, the rule is it's equal to Fn minus 1 plus Fn minus 2, right? Because it starts for n is greater than 1. So any number greater than 1, the way to find the number is to get Fn minus 1 plus Fn minus 2, right? So for, let's say, F2 is equal to F2 minus 1 is 1 plus F2 minus 2 is 0. So F2 is equal to F1 plus F0. So we got here F0 is 0, right? And F1 is 1. So we know that F2, let me actually move my camera. We know that F2 is equal to 1, which is F1, plus 0. So F2 is equal to 1. But we need to find a way to get it into a code, right? How does a computer actually figure out how to figure this out? Because it's really easy for a computer to figure out that F0 equals 0 and F1 equals 1, because we tell it directly that if n equals 0, the answer is 0. And if n equals 1, the answer is 1. But how would a computer figure out that F2 is equal to 1, right? I mean, it's pretty easy for us to do it because we're humans and we can easily figure out that, okay, well, 0 plus 1 is 1, so F2 is equal to 1. But a computer doesn't know it off the top of its head that it's 1. It actually has to, let's go into code. I went over the naive solution, so I'm not going to talk about that anymore. But what I need to do is, now I need to do the actual dynamic programming solution. So earlier, remember, in the recursive version, the program goes all the way to the bottom of the pyramid from, let's say, an example of 4. What we do is we go down a pyramid, right? We know that to get the answer to 4, we have to do Fn minus 1, which is 3, plus Fn minus 2, which is 2. And then we go down again. Since we don't know the answer to 3 and we don't know the answer to 2, we go Fn minus 1, which is 2, plus n minus 2, which is 1. Again here, 1 and 0. We don't know the answer to this. We know the answer to this. This is 1. So we return 1. And we know the answer to this is 1. So we return 1 and we return 0. But I'm getting ahead of myself because the first thing we do is this. We don't know 2. So we have to go down first. So it's 1 and 0. Okay? So now we can go down. We know the answer to 1 is 1 and 0 is 0 because these are our base cases. This is what we know already, right? So we return 1 and 0, add that together, that's 1. So this is 1. We return 1 here. And now we know the answer to all this layer. So we return this, we go up. This is next to return. So 1 plus 1 is 2. Now we know the answer to 3. So it's 2. 3 is 2 and 2 is 1. So we return both of these, and now we know both of these, so we add both of them together. 2 plus 1 is 1 for 4. 2 plus 1 is 3 for 4. So that's how we do it before. But notice a little bit of a redundancy here. How do I show this? 2. All the way up here, we needed to calculate what was 2 way up here, but we also needed to do it again here. This is a horrible solution. A way better solution would be something like this. So let's say for a computer, right? Because for us, it's really easy, right? But for a computer, it would be something like this. 4, I don't know what that is. Let's see what 3 and 2 is, right? I don't know what 3 and 2 is, so let's do 2 and 1. So 2 has to be figured out. So 2 goes to 1 and 0. Okay, we finally made it to our base cases, so now we can return our answers. So 1 and 0. Add those up together, that is 2. A great way to make this solution is to actually store the solution to F2 somewhere different, like a dictionary. So we're going to make a dictionary called memo, because this specific strategy of coding is called memoization. Maybe if I can write it down, it's called memoization, right? So I'm going to make a dictionary called memo, just so it's easy to remember. So memo equals dictionary. It's an empty dictionary when we first call it, right? But basically, what we're going to do is when we figure out the solution to something else, we're going to add it. So we figured out the solution to 2, right? So 2 goes into memo 2 as 2, right? So now next time we have a 2 here, spoiler alert, it's this time, we're gonna know what it is. Let's not get ahead of ourselves. Let's just go back to the order of things. So here we have this layer, this layer. So this, we know this one, it's 1. So 2 plus 1 is 3. So 3 is equal to 3. Awesome. But now we know this one. We've done this one, so we can return it. But now we have to do this one. It's 2. So now we check if it's in memo. And guess what? 2 is in memo. So now we know that we can return 2 from here. So now we move this here. And now it's 2. So 3 plus 2 is 5. So 4. And what we would do, I mean, if this was a larger pyramid, is we'd add 4 to memo, right? So 4, 5. So you see how this works, right? See, it's basically like a line going this way instead of a whole like branch going down here and down there. Like it's just a line. So unfortunately, I did it before I actually coded it, so I should have coded it first, but this is how it works, right? Hopefully that makes a lot of sense. I think it makes good sense, but we'll see. So let's actually try programming it. So this solution requires the use of a dictionary. We're in Python, so we'll see. We make a dictionary called memo here. Memo equals empty dictionary, right? Or maybe not empty. We'll start it with 0, 0, and 1, 1. Right? That this is, remember, this is our base cases. So we start with knowing that if n is 0, we return 0, and if n is 1, we return 1. But what we're gonna want to do is we're gonna say if n is less than or equal to 1, we're going to want to return n. Okay, honestly, it's not really necessary to have it in the dictionary since n is returnable itself if it's less than or equal to 1, right? Since 1 and 0 are the same thing as their solutions, so it's not really necessary to have it in the dictionary. Now, we have to see if n is inside the dictionary already, right? Because what we're going to want to do in this solution is store the solution inside memo and then return it if it's available, right? So if n in memo, which means that the solution is already inside this dictionary, then we're going to just want to return the answer at the index of n, right? Of n, right? Because the answer at the index of n is going to be the solution. And the reason it's in red right now is because I haven't done self yet, right? I think self, is it self or memo is not defined? Well, it's right here, so okay, there it is. Oh yeah, I don't need, sorry, I'm used to Java, so here we go. So check the base cases. Now we check if it's in memo already. If it is, then we just return it. And if it's not, we have to put it in. So how do we put the solution to a certain question of n if we don't know what it is already? Well, we do what we did in the first solution, which is just go down the list, go down the path, and return it. So memo n, sorry, self, I'm new to Python, I'm sorry. Self memo n is equal to fib n minus 1 plus fib n minus 2. One thing I'm not sure about though is it important the order of fib, right? Like, does the n minus 1 go before the n minus 2? Would it make it faster or would it not? Actually, I have no idea. So what this does is it basically makes it go through itself again and check the previous two solutions and see if they're in it and then return themselves. So it knows what it is in memo, right? So now we return memo n. Let's see if this works. Okay, something, oh, self, sorry, self again. Run. And it passed, right? Accepted. You should be able to see everything. It's been accepted. So let's submit it. And it's accepted. Please don't look at the runtime error. Okay, regardless, this is the dynamic programming solution. Yeah, sorry, that's it for today. That's everything. So goodbye.